everybody. Good morning, good evening, depending on where you are joining from. We are live from LF AI and Data TAC Talks. Today, we are going to talk about a special topic, and it's a project that we recently incubated at the Linux Foundation's AI and Data Foundation. Quick reminder: our TAC Talks are meant to have project presence. We talk about our projects from LFAI and Data Foundation, their architecture, technical details, and how to get involved in the community. So today, with me, I have Robert Shaw from Red Hat, who is going to speak about vLLM. So super excited to host Robert. And for myself, I'm Vinny Jaiswal, your host for TAC Talks and the chair of Technical Advisory Board for Linux Foundation AI and Data. So let me give the floor to Robert to do some introduction. Robert.
Hey, thanks for having me on today. Really excited to be here and chat about vLLM. Just for background on myself, I'm a director of engineering for Red Hat. Recently joined Red Hat about a month ago as part of an acquisition of Neural Magic, which is the company I was at before. Neural Magic was one of the biggest contributors to the vLLM project. I'm also a committer on the project, and I'm also on the TAC committee for LFAI and Data. So it's really nice to be here and chat more about vLLM.
Yeah, that's an amazing progress. What happened in last few months, ever since vLLM got open source, donated, and then acquisition happened. So super exciting, and with all the things that are going in Gen AI and model world, I think this makes up as an amazing topic for our TAC Talks. So Robert,
sorry, I'm getting some feedback.
So why not from that?
Sorry, could you repeat the question? I got some feedback on the internet.
Yeah,
Hey, Vinny, I think your internet is going in and out.
I think you can share.
All right. All right, so maybe we can dive into vLLM. Carly, would you mind sharing the slides? All right, great. Cool. Can you guys see slides? Yep, looks like we are. Okay, cool. So having some internet challenges, but we'll dive right into the main agenda, which is vLLM. So maybe to just step back, I wanted to talk about the original problem that vLLM is trying to solve. So when vLLM first came out in 2023, the summer of 2023, we were in a situation where serving LLMs was really, really slow and really, really expensive. So prior to vLLM, a single A100 GPU, which was really the top GPU at the time, could only serve less than a request per second. And this is for a pretty moderately sized model, 13 billion parameters and a moderately sized input. And so what this really meant is that a lot of GPUs would have been required to build production scale LLM services. And obviously, this is critical for the broad usage of LLMs that it costs low enough to justify the use cases. So we were in a pretty dark world, before vLLM. And so what vLLM is an inference server that's optimized for performance, and specifically an inference server that can handle multiple requests. If you think about an LLM service, we have one kind of REST endpoint that could be called into, and hundreds, if not thousands, of clients that will be connected to that server all at once. And that inference server's job is really to take a model, which is at the end of the day a pile of linear algebra with really, really big matrices that need to be multiplied efficiently, and map that linear algebra onto a hardware accelerator that's really optimized to execute those math operations fast. And the inference server's job is to take all of these separate requests coming in at random times, schedule the work, manage the memory, and ultimately make sure that we're spending, and utilizing the GPU at really, really high rates. And this is a very challenging task because LLMs are big. There's a lot of intermediate state to manage. And as many, many requests get added to the system, the overheads associated with doing this can be significant. And so vLLM's job is really to be this bridge that connects several clients, a model, and hardware, and ultimately gets back really, really good performance, which helps to reduce the costs of deploying LLMs, which, given their given their large, can be quite significant. So let me switch to my next slide. So to understand why this is a hard problem, and especially is why it's a hard problem relative to various other deep learning models, you have to understand how LLMs work at the end of the day. So LLMs are what's called autoregressive, but really this is just a fancy word for meaning that we generate words or tokens sequentially. So what llama is at the end of the day is a probability function which takes in a set of words and gives you back the probability distribution of the next word in the vocabulary given that prior set of words. And so the way that we can use a function like this to generate text is by sequentially passing data through the model to generate one word at a time. So for instance, if we get a prompt such as artificial intelligence is, what we can do is pass that prompt to the model and use that model to predict the probability distribution of the next word. And then we sample that to generate the word the. After this, to generate the next word, we pass artificial intelligence is the to generate the probability distribution of the next word. And again, we sample the word future, and we do this over and over and over again. And so at the end of the day, this is what an LLM server is doing. It's, taking this model, which is this probability function, it's passing the incoming prompt through and then sequentially doing that over and over and over again to generate one word at a time and ultimately stream that back to the user. Now, why does this mechanism create a challenge for building an inference server? Really, the reason is that, as you can tell, each request requires multiple passes through the model. And this creates complexity because we have to manage all of this state, where a request is going to last multiple iterations through the model. And additionally, these requests can be long running. For instance, if we have a request that generates 1,000 tokens, which is not unreasonable, this can take 10 seconds to kind of process the request. And so a big piece of complexity comes in is that we can't process one request at a time. We need some mechanism for interleaving requests and enabling new requests to join the system while a request is ongoing. And so traditional strategies like dynamic batching, where requests were batched together and then offloaded to the model to execute, will really fall apart in the context of an LLM. Given this dynamic where we have to schedule work, and do multiple passes through the model to generate a single response. In addition to this, each one of these passes through the model generates intermediate states. And so a big challenge or a key optimization in LLM serving is that we don't have to recompute the entire prompt every time we want to generate a new token. So there's an optimization called KV caching, where we effectively cache the intermediate states of the query, the key and value vectors, and reuse them in between each one of these states. So if we look at a generation like artificial intelligence is the future of technology, we'll reuse the KV cache state from artificial intelligence is to predict the word the, and then we'll reuse the KV cache state that was generated in that forward pass to predict future. And we'll do this over and over again. These KV caches are very large and expensive to keep in memory. For instance, this is a Llama 2 model. This is a bit of a dated slide, but for a Llama 2 model, these KV caches can take up gigabytes per request. And so we need to really carefully manage this KV cache memory and all of these states for many requests that are processing all at once. And this is a key challenge because we can run out of memory very quickly if this isn't done properly. And keeping track of all of this state is, technically complicated, especially when we have multiple requests that are coming in at random times. So really the key innovation of vLLM was implementing something called page detention, which is an algorithm that allows us to manage this KV cache memory in a smart way. And really it's inspired by something called virtual memory from an operating system, where we maintain a mapping from logical memory to physical memory, which allows the requests to deal with the logically contiguous keys and values, but store them in non-contiguous memory space. And this allows us to have much more fine-grained management of KV cache memory while still doing the continuous batching that I spoke about at the beginning, which helps to improve the performance and utilization of the GPUs. And so as we think about an individual request inside of vLLM, these requests will deal with logical KV cache blocks that look like a request in sequential order. But these block tables will map these logical blocks to physical blocks that are actually in GPU memory, which can be in effectively completely random order, which allows us to better utilize the GPU memory and really have fine-grained control over how much memory is being utilized, which is really a key optimization for making sure that we can fit these models into the GPUs we have available. And so in terms of vLLM's early timeline, the project really started out at UC Berkeley. It was founded by Woo-Suk and Johan, who were students in UC Berkeley's Sky Computing Lab. And they really got started trying to build an inference server for OPT 175B, which was a very large model in 2022 that was an open source recreation of GPT-3. And obviously, things got a lot more interesting as ChatGPT rolled out in December 2022, and the world really woke up to the idea that GPT-style models could be very, very useful for a variety of consumer and enterprise applications. And so as they continued working on building an inference server, the original page detention paper that I spoke about was written. And some other projects in the Skylab, this project called Vicuña, which was one of the first examples of doing instruction tuning of LLMs. vLLM was really used as the inference server that powered this model service and was one of the first really interesting projects that was built on top of Llama 1, which had been released at the end of February of 2023. And so ultimately, the vLLM page detention paper was submitted, and the open source inference server vLLM was released in June 2023. After powering that Vicuña service and implementing some more optimizations to take the prototype and turn it into a real kind of first implementation of an open source LLM server. And the pain point really that got solved is at the start before this, we were doing really naive things like dynamic batching for LLMs and not managing KV cache memory properly as best it possibly could. And vLLM was really the first server that implemented this page detention optimization, which gave it really, really great performance right at the time that open source models started to come out with Llama 1 and Llama 2. And the industry really started jumping on vLLM as the place to implement all the key optimizations that have emerged and key models that have emerged over the course of the past year and a half. And so while vLLM, started as a student project at Skylab and, was built around some prototype models like OPT, it really, really, really quickly has emerged as, one of the de facto standards for serving open source models. Obviously, GitHub stars aren't the be all and end all, but really any metric that you look at, whether it's GitHub stars or PyPy installs or the number of people contributing to the project or the number of groups committing to the project or GPU usage hours from our anonymous tracking of, how long vLLM is running for, the metrics are up and to the right. And, especially some of the GPU usage hours, we've seen, things like 5 to 10x increases in the number of hours that vLLM is running for over the course of the past, 9 to 12 months. And things are really not showing signs of slowing down. And the ecosystem is really, gravitating around vLLM as the, kind of stack of choice for serving open source models.
So Robert, quick question. While you were testing this and benchmarking all the performance, what were other tools that were out there and what were they missing?
Yeah, so at the time, there had been a couple of projects that emerged. So obviously, Hugging Face Transformers is kind of the reference implementation for a lot of open source models. And so what a lot of like early inference servers kind of did is took Hugging Face Transformers and wrapped it with traditional dynamic batching servers, where the batching would happen at the request level. And Transformers is an absolutely amazing standard for training models and for reference implementations of models that the community relies upon. But it's not optimized for doing high performance batch inference serving techniques. It doesn't implement the optimizations for an inference server. So these kind of more naive dynamic batching techniques, when vLLM came out, were what folks had started to do. Additionally, Hugging Face had implemented a project called text generation inference, which is kind of Hugging Face's competitor to vLLM, which is another great project that we've learned a lot from. Which didn't have this page detention implementation at the time. Of course, now it does. And, it's another great project that we learn a lot from and, collaborate closely with. But at the time, there just wasn't a server that had implemented this page detention implementation, which, gave vLLM this really great performance advantage at, kind of its initial launch. And since then, all of the features that I'm going to talk about over the next couple of days or over the next couple of minutes, have blossomed as the community kind of standardized around, vLLM as really this open source, community owned, open community kind of project that, has allowed various different groups, including Neural Magic, but also other model providers and other hardware providers to integrate support for their platforms. It's just a very, very well-run project. And I give a lot of credit to the Skylab team from Berkeley for deliberately setting the project up in a way to encourage this type of external contribution from companies like ours and now Red Hat, as well as from hardware and model providers and even third-party contributors. Like, I think I'll show some commit rate stats at the end, but over half of our commits come from community members who are not part of any of the key organizations that are kind of making up the main code base. And this commit distribution, I think, is a very good sign of the overall health of vLLM in terms of who's developing and demonstrating that it really has kind of become this ecosystem standard for how LLMs are served.
Yes, definitely. There were a lot of LFAI projects who were interested as well. So yeah, it's exciting.
100%. 100%. And definitely the contribution of VLM to LFAI and having open governance, I think, is a very important component of this that has made it really comfortable for us at Red Hat and us at Neural Magic to be involved with the project. Just knowing that it's kind of a neutral place that the project is set. It's really helped us to get comfortable with putting so much of our business behind VLM. All right. So back to the main agenda. So from that beginning of kind of being the first implementation of page attention and this original kind of setting the stage for how open source inference serving should work. Of course, VLM is no longer the only the only platform doing page attention. There's lots of other great inference servers like SGLang or TGI or TRT-LLM that also leverage page attention. But really, our goal with VLM has been to take that initial implementation and really try to build the fastest and easiest to use open source LLM inference and serving engine around. And that's really our North Star and what we kind of work backwards from. And so fastest, of course, we're highly focused on performance. This has been especially one of the key areas of investment from the VLM core committer group over the course of the past 6 months, as we've tried to address the performance overheads and really try to bring best-in-class performance into VLM. This has been a huge focus area. And with ease of use, we want to make it as simple as possible for users to both deploy the latest and greatest models that are being implemented, but also to take advantage of all of the amazing research that's being done to optimize LLM serving, and really trying to take all the best methods that are emerging in research papers and incorporate them into VLM. So I'll talk through some of the features that we've incorporated over the course of the past year, over the course of the past year and a half. So to get started, in terms of ease of use, the main thing that we have in VLM is 2 key APIs for how to interact. The first is a Python interface, which is primarily targeted at offline batched inference. We leverage Hugging Face Transformers models. So one of the real key advantages of VLM is that we can simply deploy the model in the format that it's typically released in and that it's typically fine-tuned in. So we deploy Hugging Face stubs or local directories of Hugging Face models. And we have a Python interface that enables VLM to run inside of typically batch workloads, that might be orchestrated by some higher level framework. In addition to this, VLM offers an OpenAI compatible API server where we can serve the model and interact with it as a REST service. And this conforms to the kind of industry standard protocols that have emerged for completions and chat completions. And ultimately, we're continuing to push on expanding this to support embeddings and whisper transcriptions, et cetera, et cetera. And we've had some great contributions from the community, especially around some more sophisticated capabilities in the API server, such as tool calling and JSON structured output. So we really support the full gamut with the OpenAI server. But in terms of our journey through adding more and more features to VLM, I just wanted to hit on a couple of key areas, which is model support, hardware support, performance, some of the engine capabilities, our distributed system architecture, and the open source community, to just give a flavor of some of the capabilities that have been added to vLLM since the original page attention implementation. So to get started with models, one of the challenges, but also most exciting parts about working on VLM is the breakneck pace at which the open source model ecosystem is emerging. All of the model vendors continue to innovate and bring in new capabilities to their models, whether it's performance optimizations like MOEs that players like Mistral have added with their Mixtral model, or it's especially the flavor of the day with the recent DeepSeek V3 release, which is a mixture of expert models. This is one kind of category that we have supported well in vLLM relative to the initial, kind of more GBT llama style models. A key area that has become increasingly important over the course of the past 6 months is multimodal models. We've seen a ton of this over the past 6 months, starting with the Lava architecture, which is built on top of Llama, but also from Mistral Pixtral, models like QuenVL from the Quen team, and even multimodal Llama with the 3.2 launch over the course of the past year. And vLLM has had really first-class support for multimodal models for a long time, and this has been a huge focus area, for instance, in our V1 architecture, which you can check out the vLLM blog for some details on how some of the recent innovations we've launched. But multimodal has been one of the key real areas that's challenged us and pushed us on our APIs. And so it's been great to kind of keep up with this kind of current innovation. Additionally, there's been a lot of innovation in trying to improve attention performance. Some of you may be familiar with things like Mamba, which are examples of linear attention modules, which kind of breaks the ON squared scaling that occurs with more standard transformer architectures. So both regular state space models with examples like CodeStrol Mamba are supported inside of vLLM, as well as hybrid transformer models, which mix between the state space and the attention layers, such as Jamba, are supported in vLLM. And then recently we've been pushing on adding support for non-generative architectures like embedding models or reward models. But ultimately, it's really our goal to make sure that model providers see vLLM as a key strategic area for them to invest in. And we invest a lot of time in making sure that we can support the latest features that are coming out in new models. Examples of this are things like DeepSeek V3, which implements something called multi-latent attention that helps to reduce the KV cache sizes. This is an example of something that we will work very hard on to enable this feature such that the models can run well in vLLM. Another example with that we will likely start working on is DeepSeek launched a model called Janus yesterday, actually, which does text generation and multimodal generation inside of the same architecture. This is not something that we have a concept of in vLLM yet, but to just give a flavor of why this is kind of an ongoing investment area for us, the breakneck pace at which models are adding new and more features is something that we continue to invest behind and helps us to support the latest architectures. And one of the real advantages that we have as an open source project that is deliberately set up around community contribution is that we can have collaborations with the key model providers, whether this is folks like the Llama teams, trying to have support for Llama on day one release, or whether it's folks like the Mistral team or the Quen team that actively contribute support for their models and ultimately even do certain launches on top of vLLM, such as the Pixtral and Quen VL launch. Having these collaborations and the openness of our ecosystem such that these teams can make sure that the features that they want to implement in the model are supported in vLLM, it really shows the power of this open community development model that enables us to very rapidly keep up to date with the pace at which models are coming out. So this is a real advantage of vLLM, in its position in the ecosystem as a very, very popular server. And it's something that we will absolutely double down on over the course of the next couple of years, as we envision a significant amount of continued innovation in the architectures of new models. Additionally to this, hardware support is another area that we've had a lot of active collaborations with various hardware vendors. So of course, NVIDIA, AMD, AWS Neuron, CPUs, Google TPUs, Intel Gaudi. One of the real key advantages that vLLM has is, we're a PyTorch-based, project. And so PyTorch provides a really nice interface that allows us to, map some of the model definitions, the scheduling code, the utilities, all of the stuff that doesn't really have anything to do with device-specific execution. All of this is able to be shared, or most of this is able to be shared across the various hardware backends, and it allows the hardware companies to contribute support to vLLM with a relatively small amount of changes. That's relatively isolated to specific parts of the code base, and allows the model teams, the hardware teams, to really focus on the performance of their hardware platforms inside of vLLM without having to worry about, am I supporting XYZ model? Have I gotten the tool calling implementation done correctly? Am I managing the KV cache memory properly? All of this type of stuff is able to be, kind of abstracted and managed by the vLLM core committer group. And the hardware teams are able to focus more on, the performance of their hardware devices, which, is a very nice development model. And we continue to leverage some of the newest features of PyTorch to, incorporate some of the new hardware backends. And so, for instance, with Google TPU and ultimately our goal with AWS Neuron as well is to leverage Torch Dynamo, which is part of PyTorch 2 and torch.compile to capture graphs of the model execution, ultimately offload those to the OpenXLA and XLA compiler, which allows us to leverage the existing, large investments that Google has into their XLA compiler, inside of vLLM, and some of these newer features of PyTorch and torch.compile are really valuable in doing this. And so this will continue to be a big part of the story of vLLM, is continuing to improve and widen the set of hardware devices that we support in the platform. And again, vLLM's community-driven development model is something that enables this to work very, very nicely. And we have active collaborations with all of the hardware vendors to make sure that vLLM runs their devices well. Additionally to this, as I kind of mentioned, performance is a real key part of building a great inference server. So vLLM is deeply optimized all the way down to the kernel level. This has been one of the areas that's very near and dear to my heart, as the Neural Magic team, has spent a lot of time on model execution and on quantized operations, and so. Some of the areas that we support are things like quantized gems, the latest and greatest hardware that is available, such as NVIDIA H100 or AMD Instinct, or Google TPU, will offer support for lower precision computation. So if FP16 or BF16 compute has X flops available to it, the lower precision tensor cores on these devices will often have 2x the amount of flops available to it. And so by leveraging FP8 compute or Int8 compute, we're able to take advantage of these faster processing units on the devices and reduce the model execution time, which really helps to shrink down the cost of running a forward pass through the model. And very excited about the next generation of hardware with Blackwell, which offers FP4, which will be a new challenge for us to try to get even more performance out of our quantized operations. But in addition to this, there's other operations such as Group Gem, which is part of the MOE models. So things like DeepSeek v3. Group Gem is an absolutely critical optimization. So we have some Triton kernels that we leverage for this. Additionally, things like collective communications, where we're doing tensor parallel inference. We have custom all-reduced kernels that are optimized for latency that we leverage. Of course, attention. But in addition to this, various other utility operations such as rope or activation functions. We ultimately have inference optimized implementations of these that help us to squeeze out the performance inside of vLLM. Additionally to this, there's a real key optimization, and one of the challenges with PyTorch is that it is an eager execution model by default, which can introduce overheads. So we have a real key optimization in vLLM, which allows us to leverage CUDA graphs inside of vLLM where we capture the compute graph during our profiling stage, and then can execute the device code without having to, deal with the eager execution and, CUDA launch overheads inside of vLLM. And this is a absolutely crucial optimization that helps a lot with latency at, especially for 8 billion parameter models on H100, which is, of course, one of our, most important workloads. Additionally to this, we support a very, oh, sorry, go ahead.
Can you please talk about how vLLM project benefits AI applications or models running on resource-constrained environments such as edge computing?
Yeah, absolutely. I think that quantization and model optimization is like one of the best ways to, ultimately, of course, vLLM generically is a high performance system. It's targeted at getting the best possible performance on the device that it runs on, right? And so generically as a system, vLLM is very much set up to, run on an A10 and get the best possible performance on an A10 that it can, right? But in addition to this, we have features inside of vLLM that enable us to take advantage of various techniques for compressing models and, that exists. So a great example of this is quantization, another technique that's very near and dear to my heart. What quantization does is we can take the FP16 model and try to squeeze it down into a smaller precision, and this enables us to use less GPU memory and also accelerates the computation and allows us to squeeze more out of the smaller devices. And so vLLM supports a very broad range of quantization methods, across the board. So things like activation quantization, like FP8 and int8, are of course supported. But in addition to this, we do things like mixed precision inference, where we can compress the weights to 4 bits or 3 bits, which again squeezes things down and is particularly targeted at latency sensitive edge applications where the QPS rate is lower. So, the Neural Magic team contributed Marlin kernels for this, which Marlin is targeted at Ampere. Machete is the mixed precision kernels that are targeted at Hopper. And so we have, inference kernels for these lower precision, models that, are supported across a wide range of NVIDIA and AMD and Google hardware. And we're working on, Intel as well as AWS hardware, that really helps to, squeeze out the performance on the devices. Additionally, we develop a library in vLLM's ecosystem called LLM Compressor, which is a toolkit for applying quantization to models. This was also donated by Neural Magic to the vLLM project. It's the first example of an ecosystem project inside of vLLM. And so, we not only help, our users to, get benefits from quantization, we also help them to, actually apply quantization to the models. And so please check out LLM Compressor if you haven't. It's a great library. We're recently launching some great work on multimodal models in LLM Compressor. So make sure to check it out if you have some time. I'll skip over Torch Compile, but running a little bit low on time, so I'll speed along a bit through the last set here. But the last thing I just wanted to talk about is LLM serving is a very active area of research, amongst academics and amongst various organizations. And so what we've seen is over the years is new techniques emerge all the time that can help to improve performance of models. And so what we've been doing inside of vLLM is every time a new paper comes out, a new implementation comes out, we take a look at it and consider adding it inside of vLLM as a way to help our users to get more performance. A really, really good example of this is chunked prefill. There's a few different implementations of this in the ecosystem. Example is called Sarathi Serve. DeepSpeed also came out with an implementation of this at the end of 2023 called Dynamic Split Fuse. But ultimately, what chunked prefill does is it tries to piggyback, new requests coming into the batch onto existing decode operations. And this really helps to improve the overall throughput that the system is able to get because we're able to increase the amount of computation that's happening in the decode batches, which typically underutilizes the GPUs. And what you can see is, this is a bit of a dated slide in terms of where vLLM is at. This is really, really useful for accelerating performance at high QPS rates. And in fact, chunk prefill is one of the key optimizations that we enable by default in the new vLLM v1 re-architecture. So this is a great example of a research method emerging, and vLLM being able to take that technique and update our architecture to incorporate it, very, very quickly. And this is something that we will see kind of over and over again, where the new methods that are emerging, we're trying to incorporate into our engine. Another example of this that many might be familiar with is speculative decoding, which is an optimization that tries to leverage a smaller draft model to accelerate the larger model. We have support for this in vLLM as well, and there's lots of different variants of speculative decoding that have emerged, such as Eagle or Medusa. And even the latest DeepSeek v3 model actually has support for doing an Eagle-like multi-token prediction, which it's really great to see, some of these new models kind of incorporating this type of stuff. So this is something we'll continue to invest in, in our new v1 re-architecture. Additionally to this, prefix caching, which was actually one of the first contributions that Neural Magic made to vLLM. So it's very near and dear to my heart as well. Is a technique that allows us to reuse KV caches in between blocks, in between requests. So an example of this is a multi-turn prediction, and you often will see this from proprietary APIs, where if you have a really long chat history and that chat history hits in their caches, your input token processing will cost a lot less. vLLM supports this prefix caching concept. And again, we have a much better version of this in our new v1 architecture. Another technique is multi-LoRa serving, where we deploy multiple LoRa adapters on vLLM at once, and different requests can interact with each one of those LoRa adapters. Don't have time to go into this. Really exciting optimization as well. Similarly, structured output, forcing the model to generate JSON, doing things like tool calling. And recently a new package called XGrammar just emerged that we've incorporated, which makes this a lot faster. And we're continuing to focus on this in our v1 re-architecture with things like jump decoding. Of course, monitoring through Prometheus. My actually first contribution personally to vLLM was a refactor to the Prometheus metrics. So I find this very near and dear to my heart as well, just in terms of my own personal history with vLLM. But I'll kind of kick it here. The last thing I just want to mention is, the open source community of vLLM is very, very, very vibrant. Of course, the right-hand side shows a chart of, the Berkeley team's overall contribution. And, of course, the original project was all developed by Berkeley, but they've just done a really, really great job of encouraging new contribution into the project. And of course, the Berkeley team is one of the most active developers and, is driving and we're working very, very closely with them to continue improving vLLM. But they've just done a very great job of encouraging contribution from a wide range of, folks. And in particular, this red bar here that shows the community contribution, I think is one of the best, parts of vLLM, where, anyone can really take it and customize it and add the feature that they need to their use case. This development model is so powerful for driving the community forward. And it's why I'm so optimistic about the future of vLLM. And then in terms of, getting involved, we're definitely looking for new contributors. There's obviously vLLM is hosted on GitHub. So we have some good first issues. We also welcome documentation, and in general, take a look at our roadmap, which we publish publicly, and consider taking on one of the features. That's how I got started. Is I read the open roadmap, and I picked off the Prometheus metrics. I clicked on a good first issue, and I implemented it. So this is really the best way, in my opinion, to get involved with an open source project. Is just get started on some feature. It doesn't have to be the biggest thing, but starting your development journey is really key. We have a
I wonder what were you trying to solve, Robert, at that time?
What would you
I
say?
wonder what use case you were trying to solve at that time, which piqued your interest.
Yeah, no, I mean, at the time, like I had already decided that, we were going to be betting on vLLM at Neural Magic. And I was trying to figure out the right way for us to get involved with the community and start, engaging. And so, I wanted to implement something that I knew. I knew how to do Prometheus. The folks working on vLLM didn't really know how to use Prometheus at the time. And so I just picked off one of those issues and made a contribution. And the rest is really history from there. And since then, Neural Magic has gotten more and more involved with the project and taken on bigger and bigger role in the community. But I really think that this development model of being open and welcoming contribution is one of the best parts of vLLM. It's a very friendly community. Like no one's going to yell at you if you implement something poorly, and people are generally very helpful. We have a CI/CD and we run a lot of tests, so you're not going to break something. But really would just encourage folks to get involved. And really the vLLM developer Slack that I have listed here, you can see it on our GitHub if you can't find the link. But this is where all the development activity happens, and this is where we all communicate. So we have questions there, we have a contributors section there, we have special interest groups for various key projects. Consider joining those and just kind of reading through the channels about what people are talking about, ask questions. There's tons of people there. It's a very, very, very active Slack, and it's targeted at development more than it is at community support. So I think that this is really the best place for your day-to-day in terms of getting involved with the project. We also have the Neural Magic blog, which covers a lot of interesting topics that I've covered today, particularly around model optimization and performant inference. Also, there's the vLLM blog, which covers our recent V1 release, as well as other ecosystem projects. For instance, one of the folks that I work with at Red Hat, recently did some content about vLLM being integrated into Llama Stack, which is another great open source project that's building, a framework for building generative AI apps. So that's another kind of example of, how you can stay up to date with what's going on. We also have a bi-weekly office hours hosted by Neural Magic. We typically have, or now Red Hat, we typically have, in those office hours, a special topic that we go into more detail on, but we also cover, usually recent updates from the project. And, always we'll have open forum for discussion, both for development topics as well as community support topics. Of course, there's also vLLM meetups. We've had these primarily on the West Coast on a bi-monthly basis. We have an East Coast meetup for me living in Boston. So anyone who's on the East Coast, please come by. It's going to be hosted by Red Hat, in East Coast on March 11th. So we'd be really excited to have you there. And really, if you want to get involved with vLLM, we're hiring at Red Hat. So you can reach out to me on LinkedIn if you're interested in getting involved, on a full-time basis. We're really excited to see you all and get involved.
And Robert, are there any hands-on workshops that you conduct? I believe Meetup is that venue, right?
Meetup, typically is a good place to meet with folks. We don't really have a hands-on session, but we're pretty active in terms of GitHub issues and responding there. And then, the vLLM events are a good place to meet and talk with the developers. Office hours is a really good place to, meet and talk with the developers. Slack is a really good place to meet and talk with them. We don't have an active session for all of these, but in terms of, live discussion, office hours and meetups are really the place for that. And then, for async, GitHub issues and vLLM Slack are really like the places that I think you'll get the most engagement.
That's awesome. Thank you so much. And yeah, we are coming close to the time, Robert. So are there any other?
I got a little bit excited about.
No, that's amazing because it shows, right, what got you excited, what feature you were trying to build, and it's amazing to see your progress itself, like how you were a contributor, then you became a committer, and then the journey to Red Hat. So
absolutely,
yeah, very insightful session, Robert.
Awesome.
So with that, I think we are close to the session. And thank you so much, everybody, for participating. Earlier, we had some connection issues on my end, so I apologize. This session, TAC Talks, happen bi-weekly on Tuesdays at 9 a.m. So definitely join in. And if you missed any of the previous session, it will be recorded and available live on LinkedIn and YouTube channels. So please definitely post your questions if you have any follow-up thoughts. So with that, we would look forward to seeing your contributions on vLLM. We will post the links in this session chat. So please definitely use that for getting involved in the community. So thank you so much, Robert, for taking your time and sharing your insights with the community. We hope to see you again, maybe with some other topic in the future. Thank you all.
Good. Thanks for having me on.